Hello, you're welcome into this video. This is the fourth video in the series of development of an airfoil for a front wing application for a STEM racing competition car. At the end of the last video, we built the flow domain, the external flow domain around the NACA 0009 airfoil that we chose in videos 1 and 2. The flow domain is a C-shaped domain here, and it has the dimensions such that it extends 15 chord lengths out from the foremost point of the leading edge of the airfoil, 15 chord lengths above the airfoil, 15 chord lengths below the airfoil, and indeed 20 chord lengths from the aftmost point on the trailing edge of the airfoil. In this video we're going to move on ahead and we're going to mesh these 6 regions. This file, the Ansys file, has not been saved yet. The workbench file has not been saved yet. What I have done in the intermediary, though, from the last video to this one, is I have saved the discovery file, just called it sys, which is not really required, but I've done it anyway because I might set up a secondary flow domain here and bring it into the solver through a different process for a different reason later on. If I click onto mesh here, we can drop down in the properties here. This mesh is going to be set up, it's really Ansys mechanical, I believe, for any sort of physics, any analysis, and any sort of solver process. So I'm going to double click into the mesh. We can see on the bottom left that our mesh is starting. I did not click update project before starting the mesh. If I did click update project before starting the mesh, I'll find that when the mesh screen opens up here, I will have a mesh already generated. By virtue of the fact that I did not update the mesh on this, not that I'm going to be running into any bother, but I will have to generate the mesh within this package. And as well as that, I don't believe that the name selections, the inlet, the outlet, and the surface of the airfoil will have come through. So it would have been better practice, granted, for me to have clicked update mesh really before I came into this. But nonetheless, I'm in it now, so we'll just walk around it. This could take another little bit of time for the mesh or for the geometry to come in. So what I'll do is I'll just pause this and I'll resume again when it has come in. Okay, it's come in. Didn't actually take that long to come in after I hit the pause button, but there we are. There is the shape of our NACA 009 within the flow domain, and you can see here the lightning, meaning that I must still generate a mesh. So if I click on the mesh and I click generate, it will very quickly generate a mesh in my 6 regions, and we could see what's called an unstructured mesh. This is a Ansys default mesh. Just when I click it without any controls in place, I can see the physics preferences set up here as a CFD, solver preferences fluent. That is coming by itself. The element size I can parameterize, but the default there is 57.622 millimeters. So I can maybe even just change that and see if there's any effect on it at all. Let's bring that down maybe to 6 millimeters. When I hit enter, we can now see an obsolete mesh. It doesn't really apply anymore. I can click generate and this will re-resolve a mesh on that lower element size. Let's see what we got coming in here when it comes in. Didn't really make much of a difference on it. Maybe there was a slight bit of refinement in these areas, but nonetheless it's still an unstructured mesh. If you choose to run with an unstructured mesh, it's fine. It's not as computationally intense specifically as a structured mesh. Again, that comes with caveats depending on how finely resolved your mesh is. But what we have here is areas where skewness wouldn't be great. Aspect ratios, orthogonality isn't great. A lot of things are varied, and bearing in mind within discretization, the physics are solved at the centroids of each of these elements, and for instance, from the boundary conditions, the value at the center of this mesh will be a function of what's happening, or this cell is a function of what's happening in the cells around it. The bigger them cells are, the more error that stands. to exist between the center of that and the center of that due to the large distance. And as well as that, where there are cases where neighboring cells might have areas that are greater than 1.3, 1.4 times the size of a smaller one next to it, we're introducing undue errors. It's very hard to manage that in an unstructured mesh. However, in a structured mesh, what you can do is you can tune it in specific areas. But as I said, it takes a good bit more assessment to be able to grip the structured mesh and to do it well. The unstructured mesh will work, but on an external flow problem, especially one with Reynolds numbers in the region of what we're dealing with, and between maybe 30,000 and 50,000, 60,000, 25,000 and 50,000, maybe 55,000. The effects along the wall here are fairly substantial. At the Reynolds number, the air is like honey to this here. It just it is thick, and the viscous effects are noticeable in these areas at them lower Reynolds numbers. So what we need to make sure is that what happens along the wall here is very resolved at the minute. That there will in no way capture the viscous effects that's happening along the wall. So what you would need to do is, for an unstructured mesh only, is you'd put in an inflation layer, which is a mesh control. So what I'm going to do, just for the sake of adding an extra wee bit of time into this, is I'll add in an inflation layer, show you how it's done, and then what we'll do is we'll take it out and we'll put in a structured mesh. This video might go on slightly longer. I do have a good grip on the mesh that I want to put in, so I'm not going to be faffing about with that. But the idea on meshing is that meshing, without a doubt, and if it doesn't, it should take up maybe 2/3 of all the time that you spend on your CFD analysis. A good mesh is absolutely fundamental. It's vital for good results, and of course a good geometry, a good nice tight geometry is a necessary prerequisite of even having the faintest chance of having a good mesh. But a good mesh is absolutely vital. So spend the time on it. If you have a week to do a CFD analysis, 3 days, you can spend maybe tuning your mesh and making it better, and so on. It's such an important part. So this one here will be a little bit longer, not because I'm going to spend all day meshing, but because we'll just go through a couple of different options to try to accommodate everyone who might be looking at different meshing strategies here. So for an unstructured mesh, what we need to make sure is that we have an inflation layer around this. So what is an inflation layer? Inflation layer there is a laminate or a build-up of narrow cells from the surface into the flow field. And then we can specify the heights of them cells, which is very important. So I'm going to go to insert here, and I'm going to click into an inflation. Geometry, it asks me, what do I want to inflate into? I'm going to select the face tool here, and I'm going to select that face, inflate into that, inflate into that, into that, into that, into that, into that. Now, what do I mean inflate into it? I mean inflate from the surface into it, inflate the cells into it. So this is a surface. The geometry it asks for are the surfaces you want to inflate into. Apply, there's 6 faces. I'm going to come down into the boundary. Okay, what boundary do you want to apply the inflation to? So the edge tool is defaulted onto that. I want to apply an inflation layer onto that edge of the airfoil. I'm going to hold down the control key and hit these front edges here and the bottom edge. If I can get that to be brought in. There it is there. 4 edges, apply. So I'm going to inflate onto them. Now, inflation options, I have 3 choices here: smooth transition, total thickness, and force layer thickness. What I'm going to go for here is a force layer thickness. Okay, first layer height. What height do I want my first layer to be? Well, I'm going to calculate that out based on a parameter there that's called the y, or a metric that's called the y plus. Okay, so within the CFD we can have a y plus or a y star value. I'm going to use y plus because it seems to be still the more commonly used one, even though y star has my opinion, its own notable advantages to that. Again, in certain flow regimes specifically maybe. But I have written my own function for calculating out my first layer height, which will be the height from the surface into the midpoint, the centroid of the first cell that bounds the surface within the flow field. And the function that I have written for this also calculates other various flow parameters, including Reynolds number for a given velocity. And as well as that, my boundary layer height as well, my delta, which is 99% of the free stream velocity. So within that height, that's where the viscous effects are important. So we need to make sure that our inflation layer at least meets the full boundary height. Okay, for that reason, before it starts getting unstructured out of it. So I'm going to come on into MATLAB here, and I'm going to run this function. There it is on SMD function CFD. There's y plus and y plus wall. I'm going to run this y plus function here, and what I will do is I'll make this M file available in the comment section, so feel free to use them there yourselves. I can't really mind what inputs I put in and what outputs this puts out, other than the Reynolds numbers, the wall shear stress, my delta, and so on. But what I can do is in the command, I can type a help here, and I can give me help on the y plus. If I hit enter, it brings me up the description that I wrote for it. And what I'm really looking at here is what my inputs are and what my outputs are. So my inputs is free stream velocity, the density of the fluid, obviously the air, the dynamic viscosity of the air, the boundary layer length, and the desired y plus value. So the boundary layer length will be my chord length in this one. So I'm going to put in variables for these here. Input free stream velocity, I'm going to call u. My free stream velocity in here, from a calculation perspective, my average velocity is going to be in around 20 meters per second. My max velocity is probably going to be up in around the 42 meters per second. So what I'm going to run there is I'm going to run with a 30 meter per second onto this. I'll explain the velocity again in a later video when we start talking about the boundary conditions and what they are. But we're going to run for 30 just here at the minute. Like obviously we're accelerating from 0 meters per second up to a final velocity, peaking maybe after 0.4 or 0.5 seconds when the CO2 in the canister is fully exhausted and we lose acceleration. And then we start to decelerate, obviously, as rolling resistance and drag takes us back. But over that 1 meter, we're probably going to be in around the 30 meters per second mark. Let's go for it. Let's see what we got. Density, I'm going to put on as rho. And that's going to be equal to 1.225, and of course that there is kilograms cubic meter for air. Dynamic viscosity, and call mu, and that is 1.8, I think, e to the minus 5 for air. My boundary layer length, I'm going to call that L. Boundary layer length is L, or 0.025. And my desired y plus value. Now for my, I'll call this here, I'll actually call it y plus. I'm going to put plus, actually underscore plus. I'm going to put it as equal to 0.6. Now the y plus value, it's worth looking into the theory of y plus, but for the turbulence model, the viscous model we're going to be using, and the wall function we're going to be using at this Reynolds number, a y plus of at least of a maximum of 1 is really what we want. Now the y plus will vary along the chord length, and we will check the y plus parameter after we run the solver to make sure that our y plus is below 1 over the whole length of the chord, or of the top surface of the airfoil. But what we'll do is we'll shoot out a target of 0.6 here, just to see can we resolve a height of a cell. Okay, so there's my values now. So what I'm going to do is I'm going to output values here. I'm going to put this into a square bracket. My output is my free stream Reynolds number, so I'm going to put in RE, something I want to look at. The wall shear stress, I'm going to call tau. The estimated wall distance, I'll call that Y, maybe. The boundary layer thickness is delta. And that there is going to be my function name, which is Y plus. And open up my brackets, and this one here, you can see here, U rho mu L Y plus. Oh, I have to put in R for some reason there. R is my my rate of inflation. I'm going to put that in as 1.1. I should have added that in. That's my rate of inflation on my inflation layer. So I'm going to start with a certain height, and then it's going to get progressively bigger at a rate of 1.1 or 10% greater each subsequent cell as it moves out towards the free stream. So I'm going to have U rho mu L Y plus, tab that, and of course R. All right, there we go. Let's run that, F5 that, and see how we go. Let's see, execution script Y plus as a function is not supported. All right, I'll tell you why that is. That is because my OneDrive files now at the minute are I have this paused, and what I also have these as these are on demand only, so no doubt that this here is not physically in that CFD folder. It's on the cloud and it has to be pulled down. So I will have to go to my OneDrive folder. I'll have to right click onto it, and what I'm going to have to do then is going to have to make that folder available offline or always available on my C drive. So if you bear with me, I'm going to pause that and just change that. All right, back again. Actually took it out of the OneDrive folder and I put it onto the documents folder. Documents, MATLAB, and functions straight onto my C drive because I do have my OneDrive pause here just to free up some bandwidth, so it's just not reading it through. However, I'm now reading into that C directory, so when I run this now, I absolutely can get out my values. I can see my Reynolds number for this is just over 51,000 when I'm running a velocity of 30 meters per second. My wall shear stress is 1.62 pascals, and that there is the height of my first cell is 7.6662 by that, and then the delta as well on this one here is my boundary thickness is just under just over half a mil. But look at that. Okay, the other thing that I don't have in this, which I should be outputting as well, I think is an N, now that I think of it, because that's what the R came in from. So I did only add in N and R today because I thought it would be helpful when we're looking at inflation layers. Again, if you're using an unstructured mesh, to know how many layers that you should put in at a given rate. So let me just rerun that, and again there's an N has come in. I'd need 22 layers, given that my first cell height is 7.6662 by 10 to the power minus 6, and I'm going at an inflation rate of 1.1. So if I run back into my mesh in here, I can put them in. So my first layer height, let me scoot back into MATLAB here, is 7, 3 6s and a 2. So 7.6662 e to the power, and this here is in millimeters, don't forget, where MATLAB is in meters. That's the minus 6, this will be to the minus 3 to make it back into millimeters. The maximum number of layers I want is my N value out of MATLAB, which is 22. And my growth rate in this case is 1.1. Now I can set these up as parameters if I like, and I can change them to see how they go, but that's what we're going to run with. That's what MATLAB says is going to be good. So when I've added this control in, my mesh is now obsolete. I'm going to regenerate it. And hopefully this here will fairly flawlessly add in my inflation layer, and what we should see is a very thin collection of cells there around my airfoil. So I zoom on in, let's get a wee look at what we have. What I should be able to see is 22 divisions, being that, oh, that's the first division from the surface to there. All right, that's the first division. And I should have 22 up, and these progressively get bigger. So that's exactly what that 1.1 means, is that the height of this is 10% greater than the height of this one. This one's 10% greater than the height of this one. And that carries on until it hits 22, and then voila, we're back into this absolutely phenomenally huge cell. Now, we don't have great orthogonality here because we're very long relative to our height, but that isn't detrimental in this case because our velocity is running along that path. We're running not linearly with it. Of course, there's different velocities over that height, but they should be thin enough that the velocity difference between the centroid of that cell and the one below it isn't going to vary an awful lot linear. Down here, they vary an awful lot linearly, but that's why they're so tight down there. As our velocity moves up there towards the free stream. So we're going to have a nice built profile there, velocity profile. That'll give us an unstructured mesh. Now back here, things are just going to get very bad as far as analysis go. We have no real provisions in here to adequately look at wakes or any sort of flow coming off of after the airfoil. And even up here, we'd need to make this somewhat better. Even though it's non-structured, we'd want to make that better. Because of such a jump, the pressure and velocity here are going to be so different at the centroid of that, so different from the velocity and pressure at the centroid of this one, that we're missing so much of what's happening in here, which is still a very influential region. We could be looking at the likes of separation bubbles and all types of things up there, even though they really should only be happening down here. If the bubble bursts, you'd see the effect up there. And bursted bubbles is something that we definitely want to be able to find because it's something we need to fix if it's there. But however, there you are there. That is how you do the inflation layers, and then you can bring your mesh sizing down, or you can add in other controls to bring that down. But basically that there is a very unstructured mesh. If you use an unstructured mesh, it's easier to compute, it's less computationally intense, but you must put in boundary layers, or you must account for the boundary layer by adding in the inflation layers, and that's them there. So again, I will put that M file in the chat so everybody is free to use it. Now, if I go to mesh and I go to insert and I put in face mesh in here, geometry selection, and I select these faces. I say I want to map these, right? I want to be able to map them. I hit that, and then I hit mesh, and then I hit generate. We're not going to be able to generate anything here. You see the question mark. Why? Because what we're trying to do is we're trying to put in a structured mesh now, and inflation does not work with a structured mesh. So what we need to do is we need to take the inflation out. I'm just going to delete that straight out because I want to use a structured mesh. So I'm going to hit the generate there. Oh, it's not associated. Let me just take that out. And we'll actually put in the controls first. And then what we'll do is we'll say there that we want quadrilaterals or how we want our faces to be meshed. Let's just come back to the way we were. Okay, right, so this is what we're going to do. We're going to follow the procedure there that Anthony T and Killian Thomas had used as well as so many others. Which does come up with an absolutely fantastic result. So let's just see if we can replicate that. Now this is slightly different from the ones you'll see on Anthony T and Killian Thomas's videos, in that there's in Ansys 2025B R2 and R1, and maybe it's in 24 as well. There's something additional that you need to select in this mesh in here that they didn't have to select in there. So if anyone has been trying to replicate what they've been doing on a later version of Ansys and they haven't been able to, is probably because this thing that I'll show you here has been omitted. But let's get to it. So we're going to run into insert, and let's put in some sizing. And what I'm going to do here is I want to put in edge sizing effectively on this one here. So what I want to do now is I'm going to select a number of sides here with edges. I'm going to select that edge, that edge, that edge, that edge, that edge, and that edge, right? 1, 2, 3, 4, 5, 6, 7 edges. Geometry, let's apply them. So I'm selecting them 7 edges in. Element size, not so much. I'm going to put this in as number of divisions. The number of divisions, I can't truly mind what they put in, but I think these ones, this is going down a fairly significant depth, and I want to capture the inflation layers here. And so what I'm going to do is I'm going to put in, I'm going to make inflation layers by biasing these edge sizing as opposed to specifying them. But in order to do that, I need to put in a heavy bias, but I also need to put in a relatively large amount of divisions. So hopefully we'll see what the divisions are here in a minute. So I like things that run in 60s. So I'm going to go for 360 divisions in this here. Why I like things in run 60s, I don't know. I used to like 8s, but 360 I think is brilliant. It's divisible by so many things. So let's go for it. 360 divisions on that there as well. Capture curvature, I think all that there looks okay. Growth rate, let's put in, we're going to put a bias onto this one here. I'm going to bias this one, and when we put in a bias, we have new things that come up here as well. If I take off the capture curvature on that, yeah, and take the capture curvature off, it's something that we want to do. The behavior on this one here, I think we can keep as, I think we can keep that there soft. On this one, so I'm coming into here, yeah, I want to come around this curve. I'm going to keep that there to soft for now. Hard is brilliant, it's better for structured meshing, because the squareness, if you like, in the quadratics are, or the quadrilaterals is maintained, or is done its best to maintain. Soft gives a wee bit of leeway. Let's keep it soft and see how it goes. Capture curvature, no. Bias type, yes. The bias option, the bias factor on this, I'm going to leave as a bias factor. Bias factor, we're going to put in this fairly heavy. So let's go with maybe 50, let's go 48, we'll go with the 54,000 on that. We can get a 6 into that. Okay, now when we look at that, there's all the divisions. Every single one of them lines is going to give me a square, a line coming across. Alright, that's good. But now these ones here, these are fairly coarse. Right? That's because I have a bias in it there. And then it progressively gets thinner up here. I don't want the thinness up there. I want the refined thin ones in this surface, not that surface. And the very same as that, I want all the thinness in where the airfoil is. So like I said, that one, and that one are back to front. So I selected them 3, and that's what it says, reverse the bias on them 3, apply. Now, it's important here as well that you see this blend to neighbors. Select that to no. Put that into no. Okay. That is something there that Killian Thomas and Anthony T didn't have on there, or I didn't see it in there in their setup. But that has to be in a no to try to maintain the structured nature of this mesh. All right, let's add in another size in there. Insert another sizing. And this time what we're going to do is we're going to run with this one and this one. And let me see if I can get it. There we go. That one there. Apply. Suppress type element size. We're going for our number of divisions again. This is looking at the wake. I probably don't need to go as tight as 360 on this, so I'll bring this maybe back to 300. Capture curvature, no. Behavior, this is definitely going to be hard because we're down into more squares. We don't have the curvature of this airfoil to deal with. Now that is a symmetrical airfoil, so like you possibly could have got away with hard on that, but we'll see how we go on. Hard behavior. Capture curvature, no. Bias, yes, we are going to put a bias on that there as well. Okay, bias factor on that one. Now the last one I had was, I think it was 56,000. We can bring this one down probably a good bit, because I'll bring this maybe to 600. See where we go with that. And we could see now up at the top. Yeah, we're good there. Very thin up there. I'm going to count the number of elements that I have when I eventually create this, because You know, we could be getting a wee bit too tight there. That's given two course next to the airfoil. That line there is obviously back to front, so I'm going to change that one. And this bottom one's back to front too, I can see. I'll just zoom it in so you can see it at home. It's back to front. It's getting finer as we move away. So I'm going to select that one, and I'm going to select that one. And then come on down here, reverse bias to them to apply. Blend to neighbors, no. Grand. Okay, next mesh. Right, let's add in insert and other sizing regime. So the geometry is going to be that top of the airfoil, that bottom of the airfoil and top of the airfoil, that, and the top one up here as well. What's going on up here? There we are. 4 edges. Oh, no, I'm just going to come on into the airfoil so you can see what I selected. All right. So it's just that surface in between them lines, that line there that's at that aftmost point on the trailing edge to this line here, not these front ones, okay, just the ones on the top of the airfoil and the bottom, excluding the ones there that are approaching the leading edge. Okay, apply them 4 lines onto it. These are going to be edge size and number of divisions again. And this one here I'm going to put up into, I could probably calculate this here because I want my cells to be as square as possible, and I should have I have a good idea really of what my I know what my y plus value, my intended y plus value is here, 7.6662 by 10 to the power minus 3 in Ansys. So that's what I'd like ideally my divisions to be, you know, in the longitudinal direction as well. And I know that that chord length was 25. When I pulled it back 1 mil, I'd be 24. So if I divided that there into 24, I would know how many divisions I'd actually need. So you could go to that hassle, not so much hassle, but you can go to that detail and work it out. But what I'm going to do, I'm just going to estimate this. I'm going to go for 200 to 40 divisions in there. Capture curvature, no. And I go again with hard behavior on that. No bias at all because I want it evenly spaced. I don't want more to the front and more to the back. I want them everywhere the same, and that's that. Let's go to mesh again. Oh, apologies. I need to also go down here, blend to neighbors. No. Mesh. Let's go to the next one, insert. Another sizing, and this is the last one. I'm going to take my inlet curves, and they are going to run all the way into here. So I'm going to say that, not that the air isn't running in this direction, and that's what it's going to look like. It's not like that. It's just going to marry up very nicely this kind of ever increasing layered curve through here. So we'll see how that looks. 4 edges. This is going to be a number of divisions. This can be slightly more coarse. Right, 240. Let's bring it down to 180. All right, the growth rate is fine. No behavior. Put that in as hard behavior. No bias at all. Blend the neighbors. Flipping no. All right, and finally mesh. What I want to do then is I want to put on face meshing just to map it. Select, 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 select. 6 faces I want to map, apply. What do you want to do with them? Well, it's a map mesh. Yes, I want to use quadrilaterals. Yes, constrain the boundary. No, and so on. Everything there looks pretty hunky-dory. So if I click onto the mesh, everything now is obsolete from the last one. I want to go ahead and generate this. Now, I have a lot of divisions in these here. The laptop that I'm working in, it's decent enough, but let me see, I have it charging. Oh, it did. It ran off very quickly there, quicker than I thought it would. So what we see is we have on the outset what looks to be a fairly symmetrical mesh. I know my airfoil is stuck here in the middle in the darkest section, and it seems to be in a pretty nice setup. If I look at my cell sizing, so I get very close into here, right? That there is probably very much so too tiny on that. You say, could it be too tiny? Well, I just have an awful lot of them. Let's have a wee look and see what I have. If I look at statistics here, I have over 500,000 elements in that. It's not bad, but the thing about it is this is very skewed. What I'd nearly need to do is I would have to make the divisions, these divisions here, a lot closer together, you know, to try to improve the quality of that mesh. Whereas if you compare that to the front, those are very nicely shaped ones there. Right? Obviously, as I said, it's not as critical along these areas here because that's the direction that the velocity is moving. We're not kind of crossing over them. They're running with the shape of the velocity, but I probably can add more divisions here, or else what I can do is I can reduce the bias slightly. I can reduce the bias along these ones here, albeit very slightly. If I do that though, I'll probably bring them up a wee bit. So it's probably a combination of a couple of things that I want to do here. But first and foremost, I would reckon I'm gonna put slightly more divisions in there. I wonder, is it worth doing that just now? See what's happening up here. Right, they're getting bigger. They're pinching an awful lot there. Probably reduce the inflation rate there on that one. Let me just get a wee look at this. That's all right. That's all right. Let's check this one here. This inflation rate here, it's at 54,000. Let's try that back at 48,000. Let's see what that does. Let's see how we go here. There we go. All right. This is getting longer, so I can put in more divisions that way, which I was thinking about doing anyway to deal with the very out of whack aspect ratios here. I cut them in half, and that would solve that, and that would also bring that a wee bit closer. So just for the fun of it, I'm going to put that up to 480 divisions. It's not really solid to be able to do that. I'm just putting in more computational effort onto this. I could probably cut everything in half and run it, and then look to resolve the mesh slightly, because what we also want to remember is that we need to run a mesh independent study in this as well. So what we're going to do in videos after this is run the mesh independent study and create a mesh that has twice the elements and a mesh that has half the elements, and we're just going to keep resolving there until we get a fairly good looking mesh. This front one here, what I might do is reduce the amount of divisions on this front one. I have that up to 180. I bring that down maybe to 120. See how we go. Let's try it again. Generate. And what that's going to do is it's going to open these up slightly. And it eventually does come through. There it is. There's opened it up, albeit slightly. Let's see what our statistics are just looking like now. Oh, I'm up to nearly 650,000 elements, so I have an awful lot there still. It's probably way too well resolved there at the minute. And I think a lot of the culprit, this is going to be sitting in here. 360 divisions could be heavy, and I'll go for 300 in that. So as I said, 3 out of the 5 days of meshing if you're spending a week, and a lot of it is doing this. Now I'm probably going in a wee bit heavy on it just now. Probably don't need to go to this level just at this minute until I get into mesh independences. But that said, there and back down into the 500s, still heavy enough. Looks alright out there. See what the back of the airfoil looks like. There might be some scope to see it in here now. That happening in there. even in that wake region there stands on an awful long time. It's very well refined, maybe too well refined for what I want to do. So what I might look at is on this size in here. 300 divisions might bring that back to 240 as well. Bias factors at 600, probably not too bad, but I'll bring that back to maybe 540. Alright, reducing the bias factor won't reduce the amount of cells. It'll just reduce, it'll just even out slightly, I think, the distribution of them. But this here hopefully is taking us down near the 500 mark, and it has. Yeah, so I'm going to try to run with that. There is other wee sections in here. I seem to have a big transition. That's just going to be virtue of the fact that I take more out of here, or else I add more in here. And probably what I'm going to do is the latter. I'm going to just take out slightly less of them. I'll put that down to 180. And I'm going to go one more time. That'll open them out a wee bit, make them a little bit more like that. Not that I want to, what I'm going to be doing is going to be reducing the quality of them by opening them out a little, but what I might be able to do by opening them out, I might be able to squeeze these ones here back and just get some sort of a nicer trade-off on that. So that I think was in number 3, wasn't it? Yeah, there's 480 divisions in that. That's a shorter path. I'm going to try 540 in that one now. And that's gonna, it's not gonna cut them in half, obviously, but it's gonna just shorten the distance between them two there slightly. And hopefully I'm back in around the 500,000 mark, not too much over. Yeah, 504, I'm back to where I was. All right. And the other thing is I can reduce the bias on that somewhat, because there's no need to have that so well resolved up there. Alright, so let's try that one. Is on there. Bias factor 48,000. Let's bring it back till 42,000. You know, if it has to be that well resolved up there, then the argument means that it should be that well resolved next to it. Slightly better there. It's not, you can really just see a nice even transition. It's getting there. See what the front looks like. Alright, we still have this here. Alright, so the only way to do that there is again to add in more divisions there, but we're well out of the, well, not well out of it, there's still going to be effect out there, but we're not too bad relative to in here. This is a wee bit, or maybe too well squeezed, but it is squeezed to suit the back. So the only way you can do that is maybe up the squeezing on the front, but we're already at over 500,000 elements. We'll leave it at that. And yeah, feel free to spend another couple hours in resolving that and making that better, because it definitely can. There is room for improvement there, but all in all, it's not bad. So yeah, we are at 43 minutes now. So I did say this mesh one would be going on a wee bit longer, but hopefully you were able to take out some good points out of that, or maybe some pointers, or maybe something there that has put you on a different direction that you feel was beneficial, and so on. But yeah, as always, let me know. I'm delighted to hear what you think. It helps me tune this and even deliver a better solution for my own team. So yeah, thanks very much for the time again, and we'll see you in the next video. Next video we'll be setting up for the exciting stuff, which is the solver. Okay, thank you.